Welcome to this presentation. Today we are going to talk about how to create binary phase shift keying modulation for your FPGA board. So it's a software-defined radio thing, and to do so we are going to use Python package called Amaranth. So during this presentation we're going to talk about the concept of binary phase shift keying modulation, and then we'll see an Amaranth implementation. But before diving into the details of BPSK modulation, let's see some more common modulation techniques. So the first one we're going to talk about is amplitude modulation. AM signals are radio signals which are carried by radio frequency signals here, and they are modulated in amplitude by the baseband signal you wish to transmit to the other people communicating with you. So that changes the amplitude by increasing and decreasing the amplitude of your carrier signal following the frequency of the signal you wish to send. Then there is frequency modulation. We keep the carrier signal, we have the baseband signal too, and we change the frequency at which we are sending our data following the frequency, following the amplitude of your signal. So when your signal is in the high state, the signal transmitted has a higher frequency, and when it's at the lower state, it has a lower frequency. And finally, end phase shift keying modulation is the fact that you are changing the phase of your carrier signal. Here you see you have up and down, and here instead of having up and down, it goes down and then it keeps going on. So let's see here, for example. Here this signal, the carrier signal, is the same as the modulated signal as long as the baseband signal is in this state, but when the state of the baseband signal is changing, then you see that you are reversing the phase of your signal with an angle of pi. So if you only have two different phases, it's called binary phase shift keying, but you can also have quadrature phase shift keying and many more. And this binary phase shift keying, so BPSK, is the kind of modulation that we are interested in. As we are working with an FPGA, we can't modulate nice sinusoid signals, we only can work with square signals, and so instead of having nice sinusoid like this, we have square signals like this one, and the fact that we are changing the phase of our signal is just manifested here through the fact the square signal is a bit longer when there is a phase transition. So how do we manage to make such modulation on square signals? Well, you need to use a certain architecture, which is this one. To create your radio signal, you need first to have a baseband signal and a radio signal to be modulated. The baseband signal will be provided by a linear feedback shift register. We have a video on the subject, you can see the link in the description. And we are going to generate a pseudo-random noise with this at a frequency which will be defined by a certain value, and we will use a prescaler to do so. I'll explain later how to create a prescaler. This prescaler is also used to generate the radio frequency, and by using a XOR between this radio frequency and the linear feedback shift register, which is at the baseband frequency, you get a signal where the phase changes every time you have a transition within the linear feedback shift register. So let's see how to implement this. First things first, let's code the prescaler. So we're going to create a new Amaranth class, which will be called very originally prescaler. It will extend the elaboratable class, and we'll define for it a constructor which will have several parameters such as an input frequency, which we'll call freak-in, and an output frequency, which we'll call freak-out. We'll define an attribute called ticks per period, which will be equal to the frequency in input divided by the frequency in output. We'll define a counter, the fact I'm putting a range inside the signal allows Amaranth to calculate, when we are running the script, what is the exact size that we need to contain the number we are going to give within the range. We define an output and an enable signal. Now the elaborate method, same as before, module. Now let me tell you how a prescaler works. We know that we have a certain input in frequency, and we wish to generate as an output a signal with a frequency which is different. Generally, we will have a frequency which is lower than the input frequency, and for instance, let's say we have 10 ticks per second as an input frequency for FPGA, so it would be the clock. If the clock is 10 ticks per second, if we want to generate a 1 Hz signal, so 1 tick per second, we just need to count every time we have a rising clock signal. We count up to 10, and when we reach 10, we set the value of our output to 1, and then we restart counting, and while we are counting, unless we are reaching 10, then the value of our output will be 0. So that makes a signal which gives us 1 tick exactly every second, and that's why here we use this attribute ticks per period to define up to what we should count to reach the value of frequency we want to reach. So in the synchronous domain, we add the rule that the counter will be equal to the value of the counter plus 1. And we also make sure that if we are reaching the final value, we will reset the value of the counter instead of it having to count until it's overflowing. Also, as we wish to use our enable signal to stop or start on demand the use of the prescaler, we also define that if the signal enable is set to 1, then we keep going on, or otherwise we stop. And to stop the prescaler, nothing easier than just to ask in the synchronous domain that the counter gets the value of its reset value. And if we wish it to be resetted every time to 0, we can explicitly define it here, and that's why we wrote reset equals 0. So here we have a module that is counting up to something, and now we need to define the output. So we are just saying in the combinatorial domain that the output is equal to equal to 1 when it it is reaching the number of ticks per period we defined, or equal to 0 otherwise. Once this is done, we just return the module, and we're done. So now that the prescaler is ready, we can just import the pseudo-random noise generator we created in the last video. So now it's in a file called prn.py, so from prn import everything. And now we can think about how to implement the toggle operation. So in fact we are doing the toggle operation at the same time we will be doing this mixing operation. So that's why we are going to call this class the mixer class. So within this class we need a lot of arguments, which are the arguments we need to instantiate our PRN generator, but also the prescalers we are going to use. So we need the bit length, we need the taps, we need the seed, we need the FPGA frequency, we need the frequency of our carrier signal, and the frequency of our modulation signal. In a very original way, we are just going to define the attributes of our class like this. And for now, we are done with the constructor. Let's define the elaborate method. So in this elaborate method, we need our PRN generator. And as this is already a module that we are going to integrate to our architecture, we define a new submodule. So first of all, equals new module. And then to add submodules to our module, we just write m.submodule. We'll call this submodule PRN, and it will be equal to our PRN generator. The arguments will be for the bit length and now we are going to define two prescalers, one for the radio, so it will be called presc radio. It's an instance of prescaler which has freak in and freak out as arguments, so and one last submodule now. Let's define our PRN generation. To do so, we use the combinatorial domain. And we define the fact that the prescaler module that is triggering the shift of our PRN is active. Now that we've done this, let's do the same for the carrier signal. To generate the carrier signal, we had the rules that this is fine, plus I forgot to define the output. So the output is a signal, and on every clock cycle of this prescaler, so every time we see a tick from the output of the Presc radio, we are going to toggle the value of the carrier. So we need, in fact, an output and a carrier. This rule will be added to the synchronous domain. Alright, now that we have generated our radio signal and the PRN signal, the pseudo-random noise, we can just mix them by using the method I showed just before, like it's just a XOR. So m dot d dot combinatorial domain receives the rule that the output is equal to the carrier XOR the PRN submodule dot output, and we should be fine. Before we begin the simulations, we need to correct a few mistakes I've made. So first of all, there is here I forgot the underscore. There you do not use two pipes but only one, because we are writing an operation on only one bit. And here, this is the enable signal that we set to 1. And the last thing to correct is that we should add this line at the beginning of the file so that we can run it in bash. So let's run explain BPSK, and now we can just run GTK wave on our file test.vcd. And so you see now that the top module contains some submodules, which are the two prescalers we used and the PRN generator. So we can look at the carrier signal we generated. We can look at the shift signal, and inside the PRN we can look at the value of the output here. And now, and this is one of the reasons why you should name your variable differently following the modules. If I remember well, this is output 2. So we expect output to be the output of our top module. So you see the carrier signal, you see the output of the PRN. When the output of the PRN is at 1, then the output of our module is opposed to the carrier signal. Here we receive the information to shift every 400 nanoseconds, which is the equivalent of a frequency of 2.5 megahertz. And every time there is a change in the output of the PRN generator, you see that the phase is changing. Like before, both phases were opposed, and now we have the same here as here, whereas here we had the opposition. So while this output isn't changing, we don't see any change on the output of our module. and now it comes back to the state 1, and so we see the phase shift keying. So during this presentation you had the occasion to see how work 3 modulation techniques, and you could learn how to code your own version of binary phase shift keying modulation and a mixing algorithm using Amaranth in 3 steps. First of all, by demultiplying the clock signal to create a carrier signal, doing the same to cadence the modulation, and finally create a binary version of the signal mixing operation with the XOR door. Thanks for watching.